Welcome to the Lifestar Training and Education Center. My name is Todd, and I'm glad you're joining me for this short discussion of cardiac access. You might remember from paramedic school this kind of chart for cardiac access, or maybe your chart looked a little more like this, or perhaps it looked like this that gave you nice colored in regions to tell you which was a normal axis versus right axis deviation or left axis deviation or extreme deviation. This was the chart in which I realized that when it comes to cardiac access, I don't care. Now, I was able to make that decision because I had a great paramedic instructor who said when you are shown a way of thinking about something that just doesn't work for you and your brain doesn't wrap around it, don't worry about it, find a different way of thinking about it, and move on. And when I saw this chart and I had to memorize up, 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 down, 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 and all that, I knew this wasn't for me. As the discussion about cardiac access happened in my classroom, I began to realize that I remember back from the good old days. I'm old enough to remember the invention of electricity and indoor plumbing, and I also remember in school being taught vector math. And vector math sounds complicated, and it has that scary word math in it, but in a few moments you're going to realize that you have an instinctive understanding of vector math. A vector has two qualities to it. It has direction and it has magnitude. So there's two vectors that have the same direction, but one has a greater magnitude than the other. And the direction can be expressed in terms of degrees, direction of travel, and so on. And the magnitude can be measured in a variety of ways. It can be a matter of speed. It can be a matter of kinetic energy. If you're talking about two objects colliding with each other, there are a variety of ways of measuring that magnitude. The cool thing about vector math is you can add vectors together. So if I were to add this vector to this vector, the end result would be a vector that looks kind of like this, halfway between the top one and the middle one, and you add them together, they form a third vector. I can add this vector, which has a lot of magnitude, and this vector, which has very little magnitude, and then the resulting vector would be something like that, where you'd have very little downward effect on this vector, because one vector had so much greater a magnitude than the other. So I choose to think about the cardiac axis in terms of an intersection. This is a traffic intersection. And let's say we have a little VW that weighs 1,000 pounds traveling in this direction, going 55 miles per hour. And we have here another VW that weighs 1,000 pounds traveling in this direction. Where is the wreckage from this collision going to occur if the collision happens right there in the middle of the intersection? If you add the two vectors together, you're going to expect the wreckage to wind up somewhere right around there. So what we did is we added this vector plus this vector, and the wreckage of this accident winds up there. Let's change things up a little bit, and let's say right here we have a cement truck traveling 55 miles per hour in this direction, and we have that same little VW traveling 55 miles an hour in that direction. Where is that wreckage going to wind up? Probably you're going to have a vector that looks just a little bit like that, because you have a huge cement truck colliding with a tiny VW. The VW is going to have very little impact on the direction of travel of the cement truck. Does this vector math sound anything similar to you? Anyone who's played pool has an instinctive understanding of vector math. Because when it comes to pool, you're adding vectors together in order to get the ball to go where you want it to go. So the first vector is how hard and fast do I have to hit the cue ball in this direction in order to get this vector to be the result. So you're taking the angles and the speeds in order to get the right vectors to add together and get things to happen in the order in which you want them to happen. You're just adding vectors. And adding vectors together is exactly what the monitor is doing right in this section when it prints out your axis. But I'm only interested in this one right here, which is the QRS axis. And what the monitor does is it adds together vectors to calculate that axis. So in my head, when I'm thinking about axis, what I'm thinking about is this adding together of, in this case, because it's a 12 lead, we have 12 vehicles that are all expected to collide right here in the intersection. And some of them are very big vehicles. So we have this cement truck going in this direction, and that would be your left ventricular activity. And then you have smaller vehicles like your left anterior fascicular and posterior fascicular, which are tiny vectors. And then we have another vector in this direction and another vector in that direction and another one coming from here. And when you get all 12 of these vectors added together, you wind up with one overall cardiac axis. And if your cardiac axis all added together looks like that to somewhere around there, then all the vehicles have shown up that are expected to be at the accident, and that is a normal cardiac axis. If, however, when all these vehicles collide right in the middle, and the overall axis, when you add them all together, looks like this, somebody didn't show up to the accident that we expected to be there at the collision. And so somebody who was supposed to be driving in this direction is late to the accident or didn't show up at all. And as a result, when you add all the vectors together, you wind up with right axis deviation. So somebody's missing from the accident. And if you have enough things missing and you're going in this direction, that's extreme right axis deviation. That means a lot of people who were supposed to show up to this accident didn't show up. Those vectors are all missing. Now, in the interest of honesty, I do have to say that it's not actually 12 vehicles showing up to this accident, because the only electrodes that matter in the calculation of cardiac axis are your limb leads. So all of this stuff is not in the vector math involved in the overall QRS axis. It is only the limb leads, which is 1, 2, 3, and then the augmented leads of AVR, AVL, and AVF. Bad drawing. There we go. So those 6 limb leads are all added together to get you your overall cardiac axis. But that's why the placement of the electrodes is important. Some of you pick up patients in the hospital, and the nurses have put the limb leads right here. And that is not good for calculating a cardiac axis. It might be perfectly fine for monitoring a patient, but when you're in diagnostic mode trying to figure out what's wrong with the patient, the limb leads have to be on the limbs, which means somewhere outside the fold of the armpit in this direction, somewhere outside in this direction, and then outside the inguinal folds, somewhere south of these points. So you can put them over here close to the torso, but they can't be on the torso if you want to calculate a good, reliable diagnostic cardiac axis. And that's why I can get away with saying I don't care about looking at this up and down and trying to figure out axis that way, because if you have a 12 lead with all these leads that you can do the up, down, down thing, you also have an axis already calculated for you by the monitor. Anytime you're going to have the up, down, down, up information, you're also going to have the calculated axis. And so I just look right at that number and I know what range that's in. And by knowing it's a negative 61, so we have left axis deviation, I know who is not showing up to this overall accident. In this case, we have the left anterior fascicular block. And goodness gracious, the doc in the box figured that out too. Go figure. So that's how I like to think about cardiac axis. I think about that intersection and who's not showing up to the big party. I thank you for giving me 10 minutes of your time to just look at cardiac axis from a different point of view. See you next time.